Assalamualaikum. In this lecture, we are going to start chapter number 5, and particularly this lecture will cover first section of the chapter 5, which is about area and estimating with the finite sums. So first of all, let's review the few answers of the question, what is calculus? So it is mathematics of change. You already know that. Uh, it is mathematics of tangent lines, slopes, areas and volumes. And you're already familiar with this part of the mathematics, that is calculus of tangent lines and slopes. And now in this section, in calculus 2, you will learn how calculus help us finding areas and volumes, and how can we solve problems regarding areas and volumes with the help of calculus. So calculus also enables us to model real life situations. Calculus is dynamic. Uh, it is not static like algebra and precalculus. Well, calculus is also a limit machine. And in calculus 1, you must have experienced that limit is actually the key to derive any concept in in calculus, like derivatives, even the concept of continuity is incomplete without limit. So calculus is also called a limit machine. Uh, so basically it involves three stages, that is pre-calculus, algebra, mathematics process. In this we build blocks to produce calculus techniques, and the secondly limit process, which is the stepping stone to calculus, and finally the calculus is known as differential calculus and integral calculus. The major two branches, differential and integral calculus, and they depend upon derivatives and integrals respectively. And we have already done with the derivative part of the calculus. Now onwards, we'll do integrals and the applications. So what is the difference uh, in life with calculus and without calculus? So let's see. If without calculus, what we can do, if we have a graph of a function, we can find the height of the curve at any point in the domain, say x is equal to c. But if we know calculus, and function is not defined at some point, but still we can find the limiting value of the function as x approaches t. Now without calculus, if we are traveling from one point to another point, then we can find an average speed or average rate of change uh, of the distance with respect to time. But in calculus, we can find instantaneous rate of change at any point t is equal to c. Without calculus, we can find slope of a fixed line by using the formula rise over run, but calculus helps us calculate the slope of the line even when the shape of the line is always changing. That is, we can find the slope of the curve at some point. And without without calculus, we can find the areas of some specific uh, shapes, like rectangles, like trapeziums, like triangles, like circles. But calculus allow us to find area of uh, shapes like this, or area between two curves, or area under the curve above x-axis bounded by the lines x is equal to a, x is equal to b. So let's see how does calculus help us solve these area problems. So this is the basic problem in this section we are going to discuss, that we have to find this area of this region. Now, what is this region? First of all, this region is bounded by this curve, which is the curve of the function y is equal to 1 minus x square, and we have to find area under this curve above x-axis bounded by the lines x is equal to 0 and x is equal to 1. That is, we have to find the area under this curve from 0 to 1, right? So how to do this? We'll start with the basic shapes, and we'll try to convert this irregular shape into some regular shapes, or the sum of regular shapes, and we'll try to approximate the area of this region by doing that. So let's see how it works. So first of all, what we did, uh, we are going to split this interval 0 1 into two equal intervals. Okay, so the first interval, the first subinterval is of length 0.5, and the initial point of the interval is 0, and the terminal point of the interval is 0.5, and the second interval starts from 0.5, ends at 1. So this is how we subdivided the interval 0 1 into two subintervals. Now next, we'll draw rectangles using height of the function. Okay, now in this interval, uh, 0 0.5, we can see there are different heights of the function. So this curve shows the heights of the function at different points in the interval. Now we choose uh, highest value of the function in this function to make this the rectangle. Okay, so now this rectangle has width equal to length of the interval and height equal to value of the maximum value of the function in the interval. Now next rectangle is drawn in the same way. Um, in this interval, length of the interval is same, which is 0.5. So width of the rectangle is same, that is 0.5 or 1 by 2, you may say, and height of this rectangle is the maximum value of the function in the interval. So maximum value of the function in this interval is 3 by 4, which is at x is equal to 1 by 2. Now we can approximate this area of the region R by adding the area of these two rectangles. Now how to find area of rectangle? Area of rectangle is width multiplied by the length. Now width in this case is the length of the interval, and uh, length in this case is height of the rectangle. So let's see. So area, approximate area of this region R using two subintervals or two rectangles. We have 1, the area of rectangle 1 plus area of rectangle 2. Now area of rectangle 1 is 1 multiplied by 1 by 2. Area of rectangle 2 is 3 by 4, because height of this rectangle is 3 by 4, and width of this rectangle is 1 by 2. So 3 by 4 multiplied by 1 by 2, and by simplifying it, we have area is equal to 0.875. Of course, this is approximate area, and you can see there is a lot of error, right? Again, we try more rectangles. That is, we subdivide this interval 0 1 into 4 sub intervals in order to reduce this error. Okay, so again we'll use the same method to form these rectangles. Now since we have divided the interval into 4 equal parts, so length of one interval will be 1 over 4. And in general, length of the interval is b minus a. If interval initially is ab, then the length of the subinterval is equal to b minus a divided by number of rectangles. Okay, so see, in this case we have two rectangles, then the length of one rectangle or length of one subinterval is 1 minus 0 divided by 2, that is 1 by 2, and in this case 1 minus 0 divided by 4, that is 1 over 4. So again, in order to construct the rectangles, width of the rectangle is the length of the interval, which is 1 over 4 in each case, and height of the rectangle is the maximum value of the function in the interval. okay, in respective interval. So in first interval, maximum height is 1. So the triangle drawn in this interval has height is equal to 1 and width is equal to 1 by 4. So area is equal to 1 multiplied by 1 by 4. Similarly, in this interval, height is equal to 15 over 16, and which is at x is equal to 1 over 4, and area is 1 over 4 multiplied by 15 over 16. And similarly we can find areas of these two rectangles, and by adding all of the areas, we have this approximate area using 4 rectangles. Now in this case we have less error, but see, when we choose maximum value of the function in the interval to make the rectangle, uh, area obtained is greater than the original area, right? In both the cases we can see that area obtained is the original greater than the original area in both the cases, because we chose the maximum value of the function as height of the rectangle in the interval, and the function is decreasing. So every time maximum value of the function lied on left side or left point of the interval, right? So if the function is increasing, then the this process will reverse. The maximum value of the function will lie on the right point of the interval. So this such type of sum is called upper sum. Okay. Now this is called lower sum. This is a picture of lower sum. In this case, we have same function y is equal to 1 minus x square, and we subdivided the interval 0, 1 into 4 equal subintervals. And in order to draw the rectangles, this time we are choosing the lowest value, that is the minimum value of the function in the interval. And since function is decreasing, so it lies on the right end point of the interval. So and you can see in this case the minimum value of the function is 0, which is the value of the function at x is equal to 1. So you can see here only a line. There is no rectangle, because the height of the rectangle is 0. So we cannot draw a height of the rectangle. Height of the rectangle with 0 height, rectangle with 0 height will be just a line. So again, by adding areas of all these rectangles, we have this result. And this is also approximation to the actual area. And in this case, we have approximate area is less than the original area, right? So lower sum actually gives us the area less than the original area, and upper sum gives us the area greater than the original area. So actual area lies between the lower sum and the upper sum. Actual area is less than the upper sum, greater than the lower sum. So this is the relation between upper sum, approximation by upper sum, actual area, and lower sum. Now we can also approximate by midpoint value of the function in the interval. So in this case, we try to make the rectangles using midpoint of the interval. So again, we divided this interval 0, 1 into 4 subintervals of equal length, and the length of one interval is 1 by 4, that is 0.25. Now first of all, in order to determine the height of the rectangle, we have to find the midpoint of the interval, that is 0.125, and we can evaluate this by adding 0.25 and 0 and then divided by 2. So 0.25 plus 0 divided by 2 is the 0.125. So midpoint of this interval is 0.125. Now the height of the curve at this point is 63 over 64, and we draw a rectangle of this height. Okay, so this shows us we can choose any point in the interval or any height in of the function in the interval to uh, make the rectangle, right? So this is the midpoint. In this case, we use midpoint of the interval in order to choose the height of the rectangle in the interval. Okay. Rest is the same process, that find the areas of each rectangle and then add them up to approximate the area. By doing this, we have approximate value of the area is equal to 0.67185. And now what we did, in this case, uh, we increase the number of uh, subintervals, that is the number of rectangles. Now this is the lower sum with 16 rectangles, and this is the upper sum with 16 rectangles. And when the number of rectangles is 6, so what is the length of the one subinterval? It will be b minus a divided by 16, that is 1 minus 0 divided by 16, that is 1 over 16. So length of one interval, and we denote it as delta x. So in this case, delta x is equal to 1 over 16. So this is the upper sum for delta x is equal to 1 over 16, and this is the lower sum for delta x is equal to 1 over 16. And again, we can see that the relation between lower sum and the actual area is that actual area is greater than the lower sum, and actual area is less than the upper sum. So here is the table which shows different number of subintervals. If we choose different number of subintervals, what is the value of the lower sum, midpoint sum, and the upper sum? So this is how it works. As we increase the number of steps, that is, as we decrease the value of delta x, the approximation gets better, right? Okay. Next, if we increase number of rectangles, then approximation gets better. Okay. So there are two ways to see the same problem. That is, if we decrease the length of the subinterval, we get better approximation to the area. Similarly, if we increase the number of rectangles, and again we get the better approximation to the actual area. Similarly, this is the midpoint. As we increase the number of rectangles, we get better approximation. And this is used to do with midpoint approximation. So midpoint approximation is used to approximate this area. Now here is the figure which shows different types of sum in one frame. So you can see this is the left sum because height is chosen on the left point. This is midpoint sum because height of the rectangle is chosen at the midpoint of the interval. This is called right sum because the height of the rectangle is chosen at the right point, endpoint of the interval. So this is right. And one thing which you need to keep in mind, that the right sum is not always equal to the lower sum or upper sum. Similarly, the left sum is not always equal to the upper sum or lower sum. Upper sum means we choose maximum value of the function in the interval to form the rectangle, and lower sum means we choose minimum value of the function to form the rectangle in the interval. And right sum means we choose the value of the function at right endpoint of the interval, and left sum means we choose the height of the function at left endpoint of the interval in order to make the rectangle in the interval. So I hope this is clear now. Now again, this is another figure which shows approximation and error as well, and you can see as number of rectangle increases, error decreases. See, and 0.5% error finally we have. Okay, let's have a deep understanding of the method with the help of a question. This is question number 1 of the exercise 5.1, and we have to find a lower sum with two rectangles of equal width, lower sum with four rectangles of equal width, an upper sum with two rectangles of equal width, and lower upper sum with four rectangles of equal width. So, and the function here is fx is equal to x square, and we have to find the area under the curve x is equal to 0 to x is equal to 1. So this is the figure of fx is equal to x square in the interval 0 1. So let's see how it works. So we have to find the area under this graph. This is the graph of f x is equal to x square from 0 to 1. Okay, so we have to approximate this area, and the exact value of this area is 0.33. So let's see what happens when we follow all the instructions given in the question. So first of all, let's try upper sum with two rectangles. So there is the interval 0 1, which is divided into two equal parts, that is 0 to 0.5 and 0 to 0.5 to 1. And since this is upper sum, so highest value of the function is chosen in the interval to draw the rectangle. Okay, so similarly, for this interval, the highest value of the function is this, and this is chosen to draw the rectangle. So the approximate area under the curve using upper sum with two rectangles is 0.63. Okay, now if we have four rectangles, again we are using upper sum, and we are taking the highest value of the function in the interval to draw the rectangle for the subinterval. And now this interval 0 1 is subdivided into four parts. So the length of the one subinterval is 1 over 4. Okay, so so this is how these four rectangles are made, and the area becomes 0.47, right? Now next, lower sum with two rectangles. Now you can see that this interval 0 1 is subdivided into two subintervals, 0 to 0.5 and 0.5 to 1. Now in the interval 0.5, the lowest value of the function is 0. So that is why you cannot see any rectangle in this interval, because height of the rectangle is 0. So that is why there is a line on x-axis only. In the next interval, the minimum height of the rectangle, that is minimum value of the function in the interval 0.5 to 1, we have this much height, which is minimum height of the function. So the total area becomes 0.13. Okay, so let's try four rectangles in order to find the lower sum. So there are four rectangles again, since in the first interval 0.25, the minimum value of the function in this interval is 0. So that is why you cannot see any rectangle here, because there is a line on x-axis only. And similarly, this is the second rectangle, and third and fourth, and in every rectangle minimum value of the function is chosen to determine the height of the rectangle. So lower sum in this case is 0.25. Now we can also define average value of the function using this sum idea. So the average value of a non-negative function is defined on an interval AB as the area under its graph divided by b minus a. Area under its graph divided by b minus a. So this is definition of average value of the function in the interval AB, and where function is non-negative, keep it in mind. So there is an example. Estimate the average value of the function fx is equal to sine x on the interval 0 pi. So this is the graph of sine x in the interval 0 pi. Now what we did, we draw the rectangle in order to find the area of the region under the curve, lies under the curve above x-axis from x is equal to 0 to x is equal to pi. So we subdivided this interval into 8 subintervals. So length of every interval, that is delta x, here is pi minus 0 over 8, that is pi by 8. Okay, now we have to find the heights, corresponding heights. Now in this case the height in the first interval is sine pi by 8, and the in the second interval sine pi by 4, because this point is pi by 8, this point is pi by 4, right? This point is 3 pi by 8. So next is the sine 3 pi by 8. Now 4 pi by 8 is pi by 2. So next height is sine pi by 2. And again the height is taken at pi by 2. Now in this case what we did, we are not going to take the right value, as you would have noticed that we have taken the right value. We are trying to calculate the upper sum. So we have to find the maximum height of the function in the interval. So in the interval 3 pi by 8 to pi by 2, the height of the interval, maximum height of the interval is maximum height of the function is sine pi by 2. Similarly, in the interval pi by 2 to 5 pi by 2, okay, pi by 2 to 5 pi by 2, again maximum height is sine pi by 2. So we will repeat sine pi by 2. That is why these two values are repeated. Now the next interval is 5 pi by 2 to 6 pi by 2. Now in this portion function is decreasing, so we'll have maximum value at left endpoints. So sine pi by 2 and then sine 6 pi by 8, that is 3 pi by 4, and then the sine of 7 pi by 8. Every height is multiplied by the width of each rectangle, which is equal and which is pi by 8. So that is why we added all the heights and multiply it by pi by 8 in order to have the approximate area of the region using upper sum. This is called upper sum, using upper sum technique, and which is equal to 2.364. So average value is, by the definition of average value is the area under the graph divided by b minus a, that is the length of the interval. So area under the graph is 2.364 and the length of the interval is pi. B minus a here is pi. So 2.364 is divided by pi, and this is approximately equal to 0.753. So average value of the function sine x in the interval 0 pi is approximately 0.753. So there is the table. This column gives the number of subintervals, and this gives the upper sum estimates, corresponding upper sum estimates. Now there is an exercise. Use finite sum to estimate the average value of f. Okay, and f is given here, of f on the given interval by partitioning the interval into 4 subintervals. So given interval is 0 to, and we have to subdivide into 4 subintervals of equal length, and evaluating f at the subinterval's midpoint, and we have to use midpoint rule. Okay, let's see how to do this. So first of all, what we need to do, we have to subdivide it into 4 subintervals. That is, let's draw a point here in the midpoint as a midpoint of the interval 0, 1. So let's draw a point here as well. Okay. So first of all, we have to subdivide the interval. Okay. So then we'll find the height of, and this is how we are dividing the intervals. Okay, now we have 0.5 or 1 by 2, you may say this is 1.5. Now we have 4 subintervals 0, 0.5, 0.51, 1, 1.5, 1.52. Okay, now we have to find the midpoints of each interval in order to use midpoint formula. So midpoint of this interval is 0.25. Okay, and midpoint of this interval is 0.75. Okay, and what about midpoint of this interval? This is the midpoint, and midpoint of this interval is 1.25. Okay, again, now 1.5 and 2 intervals, so we have midpoint of this interval is 1.75. Now what we need to do, we have to find the heights of the curve at this point in order to draw. So this is the height at this point. Okay, so we will draw a rectangle in this interval of this height. So this is our first rectangle, right? Okay, now next midpoint is this, which is 0.75. So let's draw the height, and then we will draw a rectangle in the second interval. Okay, so this is our second rectangle, right? This is the first rectangle. Let me make them bold so that you can identify the rectangles. So this is the rectangle in the second interval. Okay, now third interval. So midpoint is somewhere here. So our height is somewhere like this, and our rectangle is going to be in this interval. This, okay. So this is our third rectangle, and similarly, the height at the midpoint is somewhere here. So we are going to draw another rectangle like this. Okay, so this is the height of the rectangle, and which is calculated at the midpoint of the interval, right? So we have to find the areas of all these rectangles, 4 rectangles, and then add them up to find the area. So how can we find the height of first rectangle? So if the R1, let this rectangle be R1, this is R2, R3, R. So our delta x here, delta t rather, because this is function of t. So delta t is 0.5, because a here is 0, b here is 2. We have to subdivide into 4 subintervals. So 2 minus 0 divided by 4 is 0.5. So delta t is 0.5 in this case. That is, the width of every rectangle is 0.5. Okay. Now to find the height, we have the height of rectangle 1 is equal to f 0.25. Okay, because the midpoint of the first interval 0.5 is 0.25, so f 2.5. Okay, similarly r2 is equal to f 0.75. Okay, and height of r3 is f midpoint of 1.5 interval is 1.25. Okay, and of r4, height of r4 is value of the function at 1.75. And you can calculate it yourself. I will just write the answers. uh, f of 0.5 is 1, f of 0.75 is again 1, and f of 1.25, and let me do the steps so that you can see what we are going to do. We are just plugging in these values into this function. So let me do 1 completely. 1 plus sine square pi multiplied by 1/25. Okay, so this is the case, and answer is equal to again 1. Okay, so this is equal to again 1.75. So this is actually 1/2 plus 0.45, 0.25 is 1 by 4. Okay, you can write as 1 by 4. So this is 1 by 4, this is 1 by 2, this is 1, this is 1 plus 1 by 4, right? 3 by 4, and then this will become 3 by 4 plus 1 by 4, that is 4 by 4. So similarly you can find the values uh, in terms of rational form as well. So this is the decimal form, and you can find the values of these points, like in fraction 0.25 can be written as 1/4. So for your convenience, so that you can find the multiples of pi in order to find the sign. So let me write it in that way. In this case, this will become 1/2 from formula, and 1.75 is actually 7/4. Okay, so sine square 7 pi by 4. Okay, and this is equal to, now the multiples, odd multiples of pi by 4 actually gives us always square 1 over square root of 2, positive or negative. So in this case this is negative. Let me solve this. 1/2 plus minus 1 over square root of 2 square, and answer is 1. That is why you can see the answer of every value is 1. Okay, so these are actually apparently they are not equal, but all are equal. So uh, because the graph, so we have the rectangles like this. Okay, similar. All right, now the area, so area is approximately equal to, area is approximately equal to 1 plus 1 plus 1, because every rectangle has height 1. So 1, 2, 3, 4, we have 4 rectangles, multiplied by width of the rectangle, which is 1/2. So 1, 2, 3, 4, 4 divided by 2 is 2. So this is the area. So average value is equal to area divided by the length of the interval, b minus a, 2 minus 0. So this is equal to 2 divided by 2. This is 1. So this is the average value of the function. So this is how you can find the average value. Okay, next application of this area, or this sum is to evaluate the distance traveled. Suppose we know that the velocity function Vt of a car that moves straight down a highway without changing directions, and we want to know how far it traveled between times t is equal to a and t is equal to b. So the position function st of the car has derivative Vt. We already know that from calculus 1. that when we differentiate the position function, we have the derivative. So we have the velocity function. Okay, so if we can find an antiderivative ft of vt, then we can find the car's position function st, right? So by setting st is equal to ft plus c, the distance traveled can then be found by the calculating the change in the position sb minus sa, so which is equal to fb minus fa. However, if the velocity is known only by the readings at various times, that is, velocity is not given in terms of function. It is given as the readings on various times of a speedometer on the car. Then we have no formula from which to obtain an antiderivative for the velocity. So, what to do in this situation? Wow. So, think what to do in this situation. So, let's see what is the solution. When we don't know an antiderivative for the velocity, we can approximate the distance traveled by using this finite sums in a way similar to the area estimation that we discussed before. So we subdivide the interval into short time intervals and assume that the velocity on each subinterval is fairly constant, and then we approximate the distance traveled on each time interval with the usual distance formula, distance equal to velocity multiplied by time, and then add all the results in the interval AB in order to find the in order to approximate the distance traveled. So this is the situation given here, and you can read it from your book in section 1. So this is not a difficult concept actually. So distance travel is equal to so this is how AB interval is subdivided into the smaller interval, and every smaller interval has the length delta t. Okay, so the distance traveled in the sub interval is given by vt1 multiplied by delta t. Okay, similarly in the next interval vt2 multiplied by delta t. So adding all these distances, we have the total distance traveled from the point A to point B. So here is an example. The velocity function of the projectile fired straight into the air is ft is equal to 160 minus 9.8 t meters per second. So in this case, velocity function is given. Velocity is given as a function of t, function of time. So use a summation technique just described to estimate how far the projectile rises during the first 3 seconds. So we have to find the distance in the first 3 seconds. Covered in the first 3 seconds. How close to the sums come to the exact value, and exact value is also given 435.9 meters. So let's see what happens. So we explore the result for different number of subintervals and different choices of evaluation points. Notice that ft is decreasing. So choosing left endpoint gives an upper sum estimate, and choosing right endpoint gives us a lower sum estimate. So first, in part A, we decided to choose the subinterval of length 1. Okay, so subinterval of length 1. That is, we have to find the value in 3 seconds. So the total interval length is 3. So sub interval has the length equal to 1. So we subdivide into 3 intervals actually. So by using, so the first interval is t1, t2, and then t2, t3, and then t3, t4 is the last interval. So we have 3 subintervals. Okay, so f of t1. So distance traveled is f of t1 multiplied by delta t plus f of t2 multiplied by delta t plus f of t3 multiplied by delta t, and adding them up we have 450, and actual is 435.9. Similarly, 3 subintervals of length 1 and evaluated right endpoints, that is lower sum. So by using the lower sum rule, we have 421.2 and actual is 435.9. See the error? And with 6 subintervals of the length 1 by 2. Okay. So estimates give an upper sum using left endpoints is this, and you can do it yourself, and I'll urge you to do it yourself. And the lower sum gives us the distance traveled 428.5. So these 6 interval estimates are somehow closer than the 3 interval estimate. So the results improve as subintervals gets shorter. Okay, or the number of rectangles are increasing. So here is the table to compare the upper sum and lower sum in case of different number of subintervals. And you can see as the number of subinterval increases, the sum gets closer to the exact value. That means error reduces. So that's all for today's lecture.